All right, so thank you so much, everyone, for being here with us today for this new reading group session organized by ContinualAI. Today, we have the pleasure to host Bilge Celik from Eindhoven University, who is going to talk about their recent work, adaptation strategies for automated machine learning on evolving data. And I think this is one of the first works addressing, very interesting ideas at the intersection between AutoML and continual learning. And so I'm very excited to hear about these very recent work and how we can push a little more, at this intersection, because I think it's very, very relevant. So thank you so much, Bilge, for being with us today. And
Yeah, thank you for inviting me.
the stage is yours.
Yes, and thanks for the invitation and being here this late Friday afternoon, postponing your weekend. Let me just start my presentation. All right. So I'm Bilge. I'm a PhD student at Technical University of Eindhoven, and today I want to present you my research, our research on adaptation strategies for automated machine learning on evolving data. So, as Vincenzo just said, it is a research that lies between two fields, automated machine learning and stream learning. And I think it makes it more interesting and also more challenging. And this is why I want to first introduce AutoML a little bit at the beginning and then talk about what stream learning brings to this problem and mention explain the adaptation strategies we developed with the results of the experiments. I hope it is not a very long presentation, and please feel free to interrupt me any moment if you have any questions. I tend to speak fast and continuous, so we'll be happy to answer. So the first question, of course, is what is AutoML? Some of you may be already familiar with it, but I will go through it very quickly. So what is the purpose of AutoML? What are we trying to achieve? The main ultimate goal is the automation of predicting a new data set with a certain budget constraint, of course. So AutoML does this by optimizing a series of operations that will transform raw data into desired outputs. These operations can be a full machine learning pipeline or a neural architecture research, not a neural architecture. In this research, we focus on the pipeline optimization, but we think it could also be applied to neural networks. And it brings us to the second question, what do we mean by optimizing a machine learning pipeline and how do we do that? There are two main problems in this field. One of them is algorithm selection, finding the right algorithm for the problem and optimizing its hyperparameters. Combined together, they form the cache problem, which is the main problem in AutoML research. So how do we change a classical machine learning system with AutoML? What we do basically is in an AutoML system, the machine learning expert that converts the tasks in the models is replaced with multi-level learning and automated optimization. This can also be done in a semi-automated way where the human is still kept in the loop and the automated system works like an assistant and the human expert can use the outcome of the system to get a better understanding of the task and improve the models with explanations. In this paper, we are going to focus on fully automated machine learning systems. So, of course, the obvious question is, so why should we use AutoML, being the human expert replaced in this loop? The main advantage is automation. So what does automation bring is automating this manual and repetitive machine learning tasks, such as hyperparameter search over different algorithms, over different data sets, otherwise that could be time consuming and repetitive and possibly accelerate these processes and maybe reduce the errors that are due to human bias and human error, provides better results because of selection of the best performing algorithm and so on. There are several studies that actually shows the advantage of automating the model design over the expert choices in many different data settings, yet so far, as much as I'm aware, AutoML has been tested very limitedly or only on static learning settings with batch data. So the question is, how would it perform with dynamically changing data? Can it adapt to the shifts, for instance, if the class distribution changes over time? Or will all these really nicely performing systems fail when there is a concept drift along the data stream? And if that happens, what are the factors that would affect the performance? And how can we adapt the current systems? So these are, in this study, we aim to answer these questions in order to gain a better insight on AutoML adaptation with online learning, and probably, possibly, for future design of fully automated online learning systems. The AutoML source space can be different in different libraries. For instance, in one library, the data pre-processing can be done manually, and then automation starts with the feature pre-processing. And in another, the data pre-processing can also be included in the optimization, and an additional meta-learning step as a warm start as a part of the pipeline that is being optimized. Source spaces can also be different in terms of the classifiers that are included or the feature pre-processors that are there. And in addition to that, machine learning frameworks that they are built on can be different, number of learners they use can be different, but the main categorization of the AutoML methods is done by the optimization method they use for the cache problem. And here is a formal definition of the cache problem. You can see that it is optimizing a training set with a set of algorithms and a set of hyperparameters for a loss function to find the optimal algorithm and hyperparameter setting over a validation set. So this A can be, instead of the single learning algorithm, A can be a full pipeline that includes data and feature pre-processing, meta-learning, or model post-processing, which of course creates a large source space of possible pipelines and configurations. That is why there is this important trade-off between computational efficiency and accuracy in AutoML. And we are going to look at three optimization approaches that are quite popular in AutoML methods. Namely the Bayesian optimization with Autosklearn, the evolutionary approach with T-pot and gamma, and random search with stacking post-processing with HDO. The cache problem was first actually handled with Bayesian optimization, and it is still one of the best performing approaches. The idea here, especially sequential-based sequential model-based optimization, is generally used when the fitness function is too costly. So you approximate it with a surrogate function that is cheaper to evaluate, and you can see that in the inner loop of the algorithm with the numerical optimization of the surrogate model. When you find the optimal solution to that, it becomes the proposal for the evaluation of the true function, which is the expansive step. And that is how the SMBO algorithms work. They can differ in the optimization criteria they use for the surrogate optimization, or how they use the observation history to model, to predict the true function, which are the prior distributions. The library we're going to use for it is the Autosklearn, which is one of the most popular AutoML methods that uses SMBO algorithm, which is specifically a random forest-based SMAC algorithm, which is found to be actually better for highly dimensional and discrete problems than the Gaussian processes. Another advantage of the SMAC is that it brings some computational efficiency because it evaluates a single fold at a time and discards the poorly performing pipelines early. In addition to the optimizer, Bayesian optimizer phase, the Autosklearn also includes a meta-learning based warm start that initiates the search for the hyperparameters for the pipelines that worked well on similar data streams beforehand. At the end, the output of the Bayesian optimizer, the learners, the optimal learners that are found, are fed into the ensemble builder, agreed ensemble selection method that will combine the classifiers together into an ensemble for prediction. Another popular approach other than the Bayesian optimization is the evolutionary computation. T-pot is one of the most popular approaches in this, popular libraries using this approach, and they use genetic programming. So how do they do that? They structure the machine learning process as a GP primitive and construct a GP tree out of it. So here you can see an example of a tree-based machine learning pipeline. The data set flows through the pipeline operators, which will add, remove, or modify the features in a successive manner. And what GP does is generation and optimization of these tree-based pipelines. So it's used to evolve the pipeline operator, as well as the sequences of the pipeline operators, as well as their hyperparameters. The objectives, it has multiple objectives of maximizing the classification accuracy and minimizing the pipeline's overall complexity, which is the number of pipeline operators in this case. They use a popular GP algorithm from the Python package deep, which follows a standard GP procedure, and the top 20% of the pipelines in the frontier is selected for reproduction with the NSGA2 selection strategy, which is also another popular approach. The output of TPOT, unlike Autosklearn, is a single best performing pipeline, and this is the one that actually gives, that is actually ever discovered according to the classification accuracy. I also want to introduce Gamma, which is another evolutionary search AutoML method, similar to TPOT, but it uses asynchronous rather than synchronous evolution, which is supposed to be faster. It also includes the semi-automated ensembling technique, similar to the Autosklearn in the post-processing step. And one other advantage of Gamma library is its modularity. So you can actually compose different AutoML systems from the subcomponents. You can extend the existing ones with new AutoML optimization algorithms or post-processing techniques. And finally, the last one I want to talk about is HTO, which is a part of the HTO framework. And it's a little bit different because it uses random grid search in a predetermined hyperparameter space. It also includes basic data processing, and for the post-processing, it trains stacked ensemble models, which is a class of algorithms that will find the optimal combination of the base learners found by the grid search before. The output of this AutoML run is a leaderboard, which is a ranked list of the optimal models, good models that are found, and any of them can be exported to be used for prediction. So all these methods perform quite well with batch data, and actually there are several studies that compare them in those settings. But with online learning, the pipeline optimization problem changes a little with several additional challenges. I'm pretty sure you're already familiar with those, but I want to go over them quickly because they're important in designing our adaptation strategies. So what is different? What changes? So models have to be trained and used for prediction without having the all training data beforehand, unlike all the batch setting AutoML systems. We need to consider that the data stream is infinitely long and has to be processed in order. And of course, only a limited part of it can be kept in memory at any given time. So with these constraints on mind, the pipeline optimization framework requires an adaptive feedback loop that takes into account the online performance of the trained models. One of the focus points of our research, and of course one of the biggest challenges of online learning, is concept drift. I don't want to go too much into detail here, since I think this group is probably familiar with the concept, but I want to underline the definition and aspects that are important in this research. There are several ways concept drift can occur, but we are interested in this research in real concept drift that happens with the shift in the posterior class probabilities, and which leads to a change in the class boundary, and this way the previous decision models becomes useless or less reliable. There are different ways to categorize concept drift based on different drift characteristics. We are interested in gradual drift and abrupt drift in this research, and you can see how they affect accuracy plots in a non-adaptive classifier, as you may be familiar with already. We also include mixed drift, a combination of abrupt and gradual drift, because it increases the complexity of the adaptation process. Again, there are several approaches for drift detection, and there are many different drift detection algorithms, and they can affect the performance of the learner differently, as you can see from the example, based on the characteristics of the data stream or the learner. One of the most fundamental ones is DDM, and there are many variations of it. In this research, we are actually using eDDM, which is an improvement to DDM to detect gradual drift better. The advantage of these approaches is that both DDM and EDDM have lower memory footprints and they require less runtime to update the statistics, which is good for an early detection of the drift. Yet, this can also be a disadvantage, and especially for EDDM, it's known that it can lead to frequent alarms at the early stages of learning, which is something we need to keep in mind when we are evaluating the results. For evaluation in this research, we are using data chunk evaluation with a forgetting mechanism of a fixed length sliding window, where the last S batches are used for training, and we forget the earlier data completely. The hyperparameters of this can be chosen, of course, based on the application. Lower values of S would require lower memory and faster adaptation, but the higher values will create larger trainings and less frequent reoptimization. So there is a trade-off, and this is what we do. So given these challenges and constraints, we come up with 6 generic adaptation strategies to automate the pipeline design for streams, especially with concept drift. These strategies can be applied to any AutoML system, so they are not application specific. And in each of these strategies, you need to run AutoML once at the beginning with the initial batch of data. I want to go through them very quickly to explain the differences. The first one is detect and increment, which includes a drift detector and checks the performance of the algorithm of the pipeline throughout the data stream. The first run of AutoML creates a model, and this model is used for predicting the upcoming batches until a drift is detected. And at that point, model is updated with the pipelines trained incrementally with the latest batches, which is the sliding window. The critical point, the difference here is the configuration of the pipeline and ensemble weights, if it's an ensemble, remains the same. So we only incrementally train the learners. For that purpose, we actually needed to limit the search space of AutoML to the pipelines with incremental learning capabilities that can continue to train on the new data. So here we assume that the initial pipeline will stay useful even in the case of a concept drift, and we only need to update the models with the new data. The hypothesis we test here is whether keeping a learner memory of the past data is beneficial for us or not. In the second one, it's very similar to the first one, but the difference is when it runs the AutoML without restricting the search space, because we retrain the pipelines from scratch. We don't keep a learner memory anymore, and we test the performance of pipeline refitting to new data without the learner memory. So in this both first 2 strategies, we actually test alternatives to rerunning the AutoML from scratch at the drift point, because that is costly. We want to understand if it is actually necessary repeating the pipeline optimization. The third one is detect and warm start, and here actually we restart the optimization, pipeline optimization, when a drift is detected. But we restart the AutoML with a warm start, which initiates the search from the best earlier evaluated pipeline configurations. So here we assume that the initial pipeline configuration is no longer optimal, yet there is still a relation between past and present, hence we keep the memory of the optimizer. Warm start, another advantage of warm start can be faster convergence, especially with the situations with small time budget situations. It can be useful. Of course, this should be the case. This should be used while the drift is not that significant enough. The fourth one is detect and restart. Similar to the warm start, again, we rerun AutoML at the drift point, but this time we run it from scratch. It is more expensive, but it could also lead to more performance improvements in case of a bigger drift. And finally, we have the periodic restart, where we rerun AutoML, but not when the drift is detected, instead in regular intervals. So here we actually test whether a drift detector is useful in pipeline optimization and whether it's actually worth retraining at certain intervals, because as you can assume, this is significantly highly costly. And as a baseline strategy, we include the train once, which runs AutoML once and uses the pipelines found at the beginning for the remaining of the data stream. And this actually tests the innate capabilities of the AutoML methods to cope with the concept drift. We do the experiments on 4 real data streams that are popular in concept drift research and 3 types of generated data streams, with each of them with 5 levels of drift magnitude. For abrupt and gradual drift, we included label noise. For us, artificial data streams are more important for the purpose of this research because we want to understand the effect of the different drift characteristics on the performance of the pipeline optimization, and this is more limited with the real data streams. You can find all the data streams available in OpenML if you search with the tag concept drift, along with the results of the several experiments. In addition to the selected AutoML algorithms, each with a different optimization approach, we also included Bagging and BLAST as a baseline online learning methods that are specifically designed for data streams with concept drift. What BLAST does is given a set of classifier, building an ensemble and determining the weights of the ensemble members dynamically based on their performance on the recent instances. And I think you are probably already familiar with Bagging, but it's an extension of bagging and boosting algorithm and simulates the drawing with replacement by retraining the classifiers multiple times on the new data. We also included GB as a baseline for incremental learning and EDDM for drift detector. So this is so far all I wanted to say. Do you have any questions maybe before I present the results? Anything unclear?
Well, it makes sense to me, but yes, if there are any questions from the audience, please speak now.
Yeah. All right, you can also ask at the end, that's perfectly fine. And it could be that I explained very clearly as well. Okay, let me move on to the results quickly. So first we look at the effect of the drift type on the pipeline optimization performance of different strategies. In the plots, you can see adaptation strategies with different colors for each of the libraries that we use for high abrupt drift. You can see that actually high abrupt drift severely affects all AutoML methods, and only some of the adaptation strategies can recover after the drift point. Again, we can also see that gamma is the first one, the quickest one to recover with the evolutionary approach. And when we look at the differences of the adaptation strategies, we can see that re-optimizing the pipelines from scratch, which is the blue line, and retraining, which is the green line, are performing quite well for Autosklearn and gamma, not so much for HTO. So this could be because of the stacking procedure, the post-processing of HTO that uses a generalized linear model, which might be overfitting on the predictions of the updated pipelines. When we look at the baselines, we can see that BLAST is quite relatively unaffected with the drift, and it's only slightly behind the best performing AutoML methods. Yet there are a few strategies that fail to recover after drift. So one of them is train once. As expected, it doesn't recover for any library. And also the incremental updating of the best pipeline, which is detect and increment, the pink line. It does recover for some libraries, but it doesn't reach the level of re-optimizing or retraining the pipelines. When we look at the high gradual drift, the best performing strategies are similar as abrupt drift, retraining and re-optimizing the pipeline. It's a little bit harder to see with the drift detected points because it detects drifts more frequently, but the blue lines, blue color and green color are those ones. And it is again not the case for the HTO. And in addition to those, we can also see that incremental learning, which is the pink line, is performing similarly to these high-performing strategies in all 3 of the libraries, actually. Warm starting the AutoML optimization works well for gamma, which is the red line, but not so much for Autosklearn. This is likely because of the Bayesian surrogate model being misled by the prior pipelines. On the other hand, Gamma's evolutionary approach manages to evolve from the previous pipelines. If we look at the BLAST, we can see that it's on par with the best performing AutoML strategies, not so much for HTO. It's better in the HTO case actually, but also Bagging is dominated by the most of the strategies in AutoML libraries. GBM does perform better, but still slightly worse than the best performing ones. Again, we see that train once is performing poorly, and periodic restart is also suboptimal, likely because the intervals of the retraining is not frequent enough, and it lags behind the gradual drift. And finally, we look at the high mixed drift that combines gradual and abrupt drifts. Again, we can see that restarting AutoML in new data performs best on all overall before and after the drift point. PRS also recovers quite well after the abrupt drift point, which actually shows that best two performing ones reruns AutoML when the significant drift occurs. Is a good idea. Compared to the abrupt data, this actually recovers faster. The AutoML library strategies recover faster in mixed drift. This is probably because of the gradual drift present before and after that triggers the drift detector more frequently. Also Bagging and BLAST also handle the drift quite well and recovers, but this time we can actually see that they are quite behind the AutoML strategies compared to the other drifts. That was the drift type. We also looked at the drift magnitude and how it affects it. So in the plots, you can see the increasing levels of drift magnitude from top to bottom. And what we can see is as the drift magnitude increases, the performance drop also increases, but the recovery period decreases. This is most likely because of the early triggering of the drift detector in high magnitude cases, because of the high fluctuations. And when we look at the strategies, we can see that detect and retrain, which is the green line, recovers usually faster than detect and restart, which is fully optimizing from scratch the pipelines. And we can also see that although reoptimization works quite well in different drift magnitudes, we can see that the performance of strategies changes as the drift magnitude changes, which is theoretically suggested, but this also shows that that is the case. I want to show a few of the real data stream results briefly because they are, as I said before, relatively less informative for our purpose. Here you can see the results for the electricity data, which is a small data stream. This is why periodic restart is just one run. And we can actually observe more variation in the behavior of the strategies with frequent drift points detected. I think in overall we can say that incremental learning is performing quite stable and quite well for all three libraries. Also, electricity dataset is known to be highly correlated, which is benefiting BLAST, and it's actually outperforming all the AutoML strategies here. When we look at the vehicle, it's a larger data stream with more gradual and less drift points. Both BLAST and also Bagging are being outperformed by AutoML. Because of the few drifts detected, the scores of the different strategies are also quite close to each other. So far, I presented the performance results of the different settings, different drift settings. After this, we actually wanted to understand why these performance differences are occurring. So what is the underlying reason? We conducted a few experiments on that, and I will briefly explain what we did. So first, we checked the pipelines at the consecutive training points. So we wanted to see if the re-optimizing the pipelines actually creates new pipelines or not. So you can see the pipeline change points with the red vertical lines and drift detection point with the markers on the performance accuracy plots. We also added detect and increment because it doesn't change the pipeline, but it only increments, it keeps training it with the new data, which is similar to stream learning algorithms. So when we look at the results, we can see that the initial run of the AutoML in detect and increment actually gives a performance boost over the Ozobegging, the baseline learner. Yet, it's still generally worse than re-optimizing the pipelines. We also see that the pipeline change points, detect and restart is actually finding new pipelines quite regularly, especially with mixed and gradual drifts. Therefore, we can actually see that re-optimizing the pipeline throughout the data stream can bring additional performance benefit over running it once at the beginning and over the baseline incremental learners, and it does come up with different pipelines. We also find, and finally, we wanted to understand the effect of drift detection, whether we are affecting the performance with this or not. So first, we did an interplay between the adaptation strategy and the drift detector. And in the plot, you can see the drift detection points for each strategy as vertical lines with the same color of the strategy. You can see that re-optimizing the pipelines leads to more drift detection points and, of course, consecutively more re-optimization and increases the performance. On the other hand, warm start is creating less drift detection points, especially after the abrupt drift, and also resulting in less re-optimization and a less performing result. And we also wanted to understand whether the drift detector we selected has an effect. And for that, we actually removed the drift detector and introduced preset drifts into the strategies. And you can see them with the dotted lines. We introduced 5 drift points to the middle, 1 to the middle, and 1 to the 2 to the gradual drift points, midpoints. And when we look at the graphs, we can actually see that there are only minor differences, although it does recover a little faster for restart. But generally, they perform quite a similar performance, which means that the drift detector does not affect probably doesn't affect the performance. And finally, we also wanted to understand why HTO doesn't recover after the abrupt drift point. And for that, we tested different libraries on the same data stream, high abrupt, with the same strategy, re-optimizing the pipelines from scratch, and pointed drift points. In the graphs, you can see that in each of the libraries, we actually detected drift, although in Gamma it's much less. And Gamma and Autosklearn manages to recover after the drift point after this drift detection. And although HTO includes the drift detection points, it fails to recover. And this actually supports our theory that probably a linear model used in HTO stacking process is not adapting that well. But we still think that HTO is competitive, especially for gradual drift cases. So this concludes my results. I want to wrap it up a little because there were so many experiments quickly. So the main goal we wanted to achieve with this study was to understand how the AutoML methods can be affected by different characteristics of the concept drift and how can we adapt them, whether we can adapt them or not. Overall, we found that the ideal adaptation strategy actually depends on the system and the characteristics of the data stream. Yet, we can also see that re-optimizing the pipelines from scratch is usually the best performing one, and it could be worth the extra computational cost that it carries. We also found that these strategies actually help AutoML techniques to recover from the drift, and they could be competitive or even outperforming the popular online learning techniques we tried. The comparisons between different AutoML methods actually show that both Bayesian optimization and evolutionary approach can handle concept drift with the correct adaptation strategy and the forgetting mechanism, of course. Yet, evolutionary approach can do this even faster by evolving from the previous best pipelines. So this we saw with the good performance of Gamma, the evolutionary approach, with the warm start strategy. We also saw that, as expected, the drift characteristics affect the learning algorithms in different ways, and you need specific adaptation strategies to optimally deal with them. Overall, it also shows that there's ample room of improvements for the existing AutoML systems, and even to design an entirely new AutoML system that would naturally adapt to concept drift while designing the pipelines. That was all from my side. You can find the paper here. I think it was in preprint. I'm not sure now if it is available. Probably it is. And I would be happy to answer if you have any questions.
Thank you so much, Bilge, for your very interesting presentation. I think, again, it's one of the first works, addressing this very interesting topic at the intersection between continual learning and AutoML. And I think this will be especially useful for real-world applications of continual learning. So maybe I can start with a simple question to you. So you concluded before that you need like different strategies, different approaches, depending on the actual data stream and the context. Do you see like a way to overcome this and try to find like a very general way of addressing the problem, or do you think that that won't be possible even in the future, and that maybe we need just a specific approach and protocol for handling this data drift and within an AutoML system, depending on the specific use cases and contexts?
Yeah, that's a very good question, and one of the first ones that popped in my head when I finished the research as well. I honestly think that the second phase, so this was my first research, based a little bit exploration, understanding how it affects. So I really think there is a need, a second level of hyperparameter optimization for this decisions as well. So I don't think these needs to be decided statically from the beginning and then see how it performs, but should be more dynamic and automated as well. So there should be another level of automated optimization that will actually keep track of these differences in data streams and basically adapt the adaptation strategy on that.
It makes sense. So like a meta-learned approach, or something fixed, that can...
Exactly, like an outer loop of the whole system,
very interesting. And then what are, if they are, there are specifics about your future work about this? I mean, do you have an idea on what to do next, or?
Yes, that was the goal from the beginning. So basically what we were trying to do is to put the batch system fit into the shoe of stream learning, which is not, it's working, it's promising, but it could be better if it was actually designed for stream learning. So I think especially evolutionary approach is quite promising. It does adapt quite naturally, quite quickly. So our second step is probably going to be creating a full AutoML system for online learning that is dynamic, doing the hyperparameter optimization dynamically, basically.
That's very interesting. It would be nice to see the results of your ideas. So do we have any more questions from the audience for Bilge?
Yeah. I did speak a little fast, but I have done this presentation several times, so that makes it quite automated.
No, I think it was great. So thank you for that. And of course, we can continue the discussions about this talk in the forum topic that they are already created. So I invite you, Bilge, if you want to share with me the slides of your talk so that I can upload them there. And of course, we can continue the discussion there if there are no questions.
I have a question, actually.
Sure, go ahead.
Yeah, I can. I think this is not discussed also like in the article or now. It was, as far as I could follow. And first of all, thank you, Bilge. It was, I also read the article before, and also following your presentation, it was really clear and very, joyful also to follow and read. And my question would be like, so these experiments and also like these ideas are, as you said, it's for online learning. So you don't want to keep the past dates. Yeah, so the past data is not kept. And yeah, also this catastrophic forgetting is not considered. So I was wondering, like, how would it affect the results, or how would it affect the even formulation of the problem if you also have like the problem of performing good in like if you changed from online learning to continual learning, so, and consider the performance of the previous tasks as well, like how would it affect? Or
I see. I mean, I would expect with the concept drift, especially with the high concept drift, to have some damaging effect on the performance, because we did kind of simulate it by the warm start. So there you actually don't forget everything, but you keep track of the previous pipelines and use it for the new search, new optimization of the pipeline as a warm start, as a initial starting point. And we did see that it did actually mislead, for instance, Bayesian optimizer quite wrongly. And when the drift is quite high, and especially with abrupt drift, it did lead to less performing, less good results for the after drift ones, though evolutionary approach did manage to recover from that. So it could be done, it could be included, but then you need something that will adapt even with the memory, basically, to the current setting.
Maybe some kinds of checks on the previous data sets as well, like if it forgot it already, or like if it is still performing good. So then yeah, some kind of checks afterwards can also lead to AutoML. Yeah.
Exactly. Yeah, there can be formed a link, and I think it could bring also some computational advantages because AutoML does take time, and this is why I emphasize that re-optimizing. Yeah, of course, obviously you can't possibly be in too much worse, but you are creating a lot of computational burden. So we were trying to, with other strategies, to eliminate this need of full re-optimization. And it could be possible. It could actually give that advantage that you can actually do this pipeline optimization much faster with this.
Okay, thank you. So it can also be promising for continual learning then. Yeah, thank you.
Yeah, I think so. Yeah. Yeah.
Are there any more questions? Oh, but maybe I can just ask you one last question, and then we can close this session. So I was wondering, do you think that would be like appropriate for the future works to also try new, let's say, well-consolidated continual learning strategies within your system, and try to see if they can help with the incremental training?
I definitely think so. This is also, of course, the learners that we include are batch learning algorithms, and that is definitely creating also, I think, a drawback, a holding back. So we are forcing them to adapt, but they are not designed to adapt. So that is one of the aspects. I've talked more about what I want to do from the hyperparameter optimization part, but also the search space definitely should be updated. And yeah, I think it will definitely give a performance boost, yeah, to the system.
Good. Maybe we have a question in the chat.
Oh yeah.
Hi, I wonder if AutoML with proxy task can be used and then separately use continuous learning techniques to solve concept drift.
You mean like sequential steps, like not combining them together? Is that what you mean?
Oh, hello. Can you hear me?
Yes.
Yep.
Oh, yeah. That's what I mean. Yeah. Thank you for the presentation. It was
my pleasure. Yeah. Could be.
Yeah, I was just thinking if
Yeah, that's perfectly fine. And I'm very open to brainstorming from the ContinualAI community, definitely. That is, I think, very useful. Could be done, though you are, I think, losing the advantage of simultaneous optimization. So if you, the idea behind this cache problem is doing the algorithm selection and hyperparameter optimization together. So that you can find the optimal combination, the optimal setting. You can separate it. It could possibly give you computational benefits, computational cost benefits, but it could also lead to deterioration of the results compared to the, well, higher level optimization, I guess. But it could be tried. It would be interesting to see if there is a big difference or not.
Because I wonder, because usually you have like a bigger data set that serves as a teacher, right? And then you have a more focused incremental changes that is like a student kind of scenario. So I wonder if the hyperparameters you found for the using AutoML for the bigger task is like a superset of the incremental changes.
I mean, I think maybe we can think about it as the strategy of train once, that we do it at the beginning and then we keep doing the incremental learning with the settings found at the beginning. It does give advantage over not over baseline incremental learner, but I think there are still advantages on keeping track of whether these pipeline settings are the optimal ones for the current data stream point or not, because of concept drift, basically. So that would depend on the characteristics of the stream, I think, whether if it's okay or not.
Okay.
But definitely would bring benefits, computational benefits, resource benefits as well. So this is why I also included something similar, and could be tried. Yeah.
Well, thank you.
Thanks.
This was very interesting. So thank you so much again, Bilge, or Bilge. How is the representation?
It's Bilge, but no problem.
Okay. No,
I'm fine with everything. Yeah.
Sorry. So thank you so much, Bilge, for your awesome presentation. I hope to see you for the next reading groups, as you all that are following these interesting events we are preparing every week at the same time. So thank you all for coming, and see you soon. Bye.
Thank you. Thank you for inviting me. Bye. See you.